let's derive the area for a sphere. So we know from previously that the circumference of a circle is equal to 2 pi r. So if we come up some arbitrary angle theta, like so, we see that the radius of the circles it starts off at capital R, which this is the radius, this is the circle that we're going to be deriving the area for, right? Well, this is the sphere that we'll be deriving the area for. But we see that the circle right there is this big, but then it gets smaller and smaller and smaller and smaller. So we need to develop an equation that relates that relationship to this smaller circle. And we're going to find the circumference of this smaller circle. And then we're going to multiply times some little element ds, right? And that will give us a differential element. If we multiply the circumference of that smaller circle times the differential element ds, we'll get a little bitty area right here, a strip all the way around. And if we sum up all the way, all along the sphere, then we will trace out the area of the sphere. And that will give us an equation for the area of the sphere. So we know also from previously that S is equal to r theta. So taking the differential, we say that ds is equal to r d theta, right? So then the area for a sphere is equal to the integral, summing up all these little areas, dA. But then the area of one of these little rings is equal to 2 pi r times ds, right? 2 pi r times ds, but then ds is equal to r d theta, right? And this is 2 pi r, yeah, that's correct. And then this is r d theta. Now, the next relationship is to find this radius, this smaller radius, as a function of theta. Well, we see that the radius of the sphere here is the same as the radius of the sphere here. And then this angle in here, this angle right here is the same as this angle theta. So we can say that this is equal to r times cosine theta, right? So then this is equal to 2 pi, and then replace this r with that, r cosine theta, r d theta. So then we have the sum, and we're going to factor out some constants. 2 pi, this r and this r become r squared, and they are constants. It's a constant value, the radius of the sphere, right? So this is 2 pi cap r squared, the integral of cosine theta d theta. Now we have two ways to do the integration. We could integrate from negative pi over 2 to pi over 2, or we could just integrate from 0, from an angle of 0 to an angle of pi over 2, right? And, from negative pi over 2 be down here, and then pi over 2 is up here. But let's just integrate from 0 to pi over 2, and that'll give us the area of this hemisphere, and then multiply times 2. So we'll integrate from 0 to pi over 2, and then multiply that whole thing times 2. So I'm going to factor this 2 all the way over. 4 pi r squared, 0 to pi over 2, cosine theta d theta. The antiderivative of the cosine theta is sine theta, evaluated from 0 to pi over 2, like so. Sine of pi over 2 is 1. Sine of 0 is 0. So this entire thing becomes 1. And 1 minus 0. So then we have the area of the sphere is equal to 4 pi times cap r squared. So this is the equation for the area of a sphere. Okay, I'm going to step this aside and give you a clear screenshot.